Presenting me, I'm a PhD student at the Institute of Physics of National Academy of Sciences of Ukraine. The topic of my work is changes of gold nanorod surface plasmon resonance induced by femtosecond laser irradiation. We will consider fast transient effects and permanent transformation of the particles. So, at first, the object of our study is gold nanorods. They're interested not only because of nano, but several reasons. They have tunable optical properties, they have polarization-dependent response, and they are interesting for ultrafast application. Nowadays, semiconductor devices work in pico or nanosecond temporal regime, while such systems like gold nanorods can work at picosecond or femtosecond regime. The study of plasmon properties of gold nanorods is pretty widespread, and we will talk more about ultrafast applications. So, usually when we are talking about ultrafast optical application, we mean transient changes of optical properties after a short laser pulse. Most papers describe this process in such way. At first, pump pulse induces intraband or interband transitions far above Fermi level, and thus create a non-equilibrium electron gas. Then via electron and electron scattering, the gas is thermalized for a time about 100 to 500 femtoseconds. And then via electron phonon scattering, the electron gas cools, and then this heat transfers to surrounding media. All these processes change both real and imaginary part of the electric function of gold. So the figure is the result of calculation from one of the last articles this year. It shows changes in the electric constants of gold after heating of electron gas. The aim of this work was to provide a complex study of such ultrafast effects in gold nanorods. Our sample was a colloidal solution of gold nanorods in water. It was synthesized at Mainz University, Germany. It was characterized by optical spectroscopy and dynamic light scattering. Here is its extinction spectra. It have two surface plasmon resonances, transverse one at 516 nanometer and the longitude at 643 nanometer. So this is like a short one nanorods. The method of study is pump probe method. We use a femtosecond laser generator amplified via regenerative amplifier. So here's a characteristic 18 nanometers wavelengths, around 150 femtosecond pulse duration, 1 kHz repetition rate, and mean power up to 1 watt. So I'll describe pump probe technique because maybe many of you don't know it. So laser irradiation is split into two beams. One beam is a pump beam. We use or fundamental or second harmonic beam, and the energy of the pulse is around 10 microjoules. So the another beam is focused into a sapphire plate, and we have generation of a white light, which is photo. This white light is presented here. It's it has wide spectral distribution, is part of the spectrum. The technical parameters are the following. The time delay that we could make for the pump and probe beam is 2 nanoseconds, and the temporal resolution is 150 femtoseconds around. For the pump, we can use a fundamental or the second harmonics with a little tuning. And the spectral range of the probe beam is from 200 nanometers to near infrared diapason. Usually we will use different plates, not only sapphire, but like HF12. So here's one probe measurements, part of them. They show evolution of surface plasmon peaks after laser excitation at 800 nanometers. So unfortunately, because of this type of measurement, they are significantly distorted because of at the region of temporal overlap there is a slight big effect of cross-phase modulation, which makes this distortion. So analysis in this part of region where the pulses are overlap is more sophisticated. Here you can see surface plasmon dynamics after 400 nanometer excitation. The influence of cross-phase modulation for second harmonic excitation is much less, so we can see changes in the peaks. Right now I will show how it changes the parameters of the peaks. So this is for 800 nanometers. We see that signal is pretty distorted. We were using a Lorentzian approximation for every measurement, and the signal is pretty distorted. We can see that after the pump pulse there is a increasing of peak width and decreasing of the peak energy, the redshift of the plasmon, and same for transverse plasmon mode and for longitude plasmon mode. These results are in good agreement with hot electron model that I was talking before, and gives electron-phonon coupling time about 3 picoseconds. But we can observe significantly different behavior of peak energy at 400 nanometer laser excitation. We can see that peak first is redshifted for a very short period of time, and then blue shifted, and then we can see some relaxation. For longitude mode, we don't see such behavior, only simple redshift. So we saw already similar behavior in copper nanoparticles in the CO2 matrix, and the author made explanation of this like at first we should consider not only changes in electronic gas properties, but also we should consider changes in the surrounding medium. So we should consider Kerr effect. The Kerr effect increases the M, and this is in cake. This reduces the plasmon peak position, so we can observe redshift. For the blue shift, there is still open questions in several articles why the blue shift, and because the hot electron model doesn't give that explanation. So the possible reasons are interband transitions, maybe they will significantly influence, and the other possible explanation is the plasma formation. The energy density is not enough to plasma formation, but due to field enhancement effects, it could be formed. So, again, about main physical mechanisms, there are changes in nanoparticles, so like increase of electron number. If we will excite with more energy photons, heating of the electron, thermalization, and cooling of this system, electron and the lattice. But also we should consider changes in surrounding media, like optical Kerr effect and formation of the plasma near the particle. And also we should remember that changes in surrounding media is strongly affected by local field enhancement. So at last I'll show reversible nanorods transformation after long measurements the optical spectra has changed from a blue one to the black one. It's have pretty simple explanation. The nanorods had melted and become more spherical, and the amount of nanorods is decreased. So the conclusions, we measured evolution of surface plasmon peak using palm probe technique, kinetics of relaxation processes in electronic gas, and also when we should take into account changes in surrounding media when we want to use it in ultrafast application. And also we saw irreversible transformation of the absorption spectrum. So the measurement was provided in the National Academy of Science for collective use laser femtosecond complex that attached to National Academy of Science Institute of Physics. Thank you.
Thank you very much. The paper is open for discussion, so perhaps you have some comments or questions. Our speaker.
In your experimental setup, could you show the setup? The line, the probe pulse is going through the beam splitter, right?
Yeah, we took part of the light, it's now shown here, part of the light to the monochromator with CCD-matrix. At one time we measure both reference white light and the white light that propagated through the sample.
How long the light is going through the glass?
Which?
I mean this beam splitter, the thickness of the glass of this.
It's a simple reflection from around maybe
1 centimeter.
No, less. It's a simple reflection from the glass. So it's
but
not,
still, the glass has a thickness.
yes, around maybe 3 millimeters.
Oh, okay, that's not too much, but still you have some. 150 femtosecond. Is it measured in the end or from the end, after the laser?
Okay, after the laser we could receive up to maybe 80 femtoseconds, and at
So
the end.
this is in the end.
Yeah.
Another question.
Very short one, thank you. Can I ask you to show one of the in slides where you mention Kerr effect of Kerr? Yes, later. And then, yeah. You mentioned that it is strongly affected by appropriate field enhancement. Which field you are speaking about? Field of crystal field, electric field.
I mean,
what field you know? Which field?
I mean electric field that enhanced around the nanoparticle.
It's your conclusion based upon which assumption may be theoretical, may be experimental, may be taken from somewhere from heavens.
About affecting optical Kerr effect, there is an article.
Yes, optical Kerr effect is, we know what's this, but I asked why you divided Kerr effect and then this influence of another electric field of surrounding.
No, I wanted to say that optical Kerr effect is affected by the presence of the nanoparticles. So it's maybe stronger than simply in the medium.
But which field you meant when we are speaking about this field effect? Approximately. Order of magnitude.
Order of magnitude?
Electrical field. Electrostatic field.
It's a laser field with the field of
The field of pump laser.
Induced. That's what order of magnitude. Order of magnitude, I'm interested in.
10 and 11 maybe. 10 to 11 watt per centimeter squared.
Okay, you have some comments?
Without enhancement.
About the cathode. Do you see this cathode if you examine the gas substrate? If you look at the normal surface without anything,
Sorry.
If you look, if you focus your laser on normal substrate, do you see also the kinetic or not?
What substrate? We use a
If you use
colloidal.
for your, panel,
We use. You're talking about sample.
yeah.
We have colloidal solution. It is in a.
If you have a solution without anything inside, do you see also the kinetic?
Mm, you mean if we will take the cell without the solution?
Yeah.
If we will see how could we see it?
So maybe.
Okay, maybe we'll talk about
Because
it
we
later.
have to back to the next. So thanks a lot once more again.